Okay, let's start. Can you just sit? Yeah. Okay, so we were discussing about expectation. So, well, I proved the. Shall we start? Okay. So I proved the following for a usual random variable. We will just do it for a random vector. So x is some random variable. X is a random variable. Okay. And it takes values in the real line. So suppose we have a function from Rn to R. Then we know that phi, I mean, by random variable, I mean discrete random variable. Okay, then phi of x is also a random variable. Then I want to prove the following. I proved it, I mean, it's the same proof. I proved it for real valued function, I mean, function from real. This is for a random, sorry, it's a random vector, sorry. But x is a random vector. Then we have a function from Rn to R. Then phi of x is a random variable, it's a real valued random variable. Then this is equal to summation phi of x1 up to xn, where x1, x2 up to xn. This is a vector in Rn. Then this is the density function, joint density function. We have already done this. It's just the same proof, and we will write the proof quickly. So E of phi of x, by definition, this is equal to summation y, then E of f of phi of x y, right? Y in R. Or we can write this as probability of. Just keep it, no? Do something. You should have finished something back. Which is equal to phi of x equal to y. This is the definition. And this is equal to same y in R. Then, I mean, we can write it as you have y here and summation of x1 up to xn. I have already given the reasoning. The reasoning is same. P inverse of this y. P inverse of y is something in Rn. Okay? It's a pre-image of singleton y, which is in Rn. Then the probability of x1 up to xn. I mean, then the probability of this x1 up to xn equal to x1 up to xn. Now you just take the summation out, and that will be just. But then this gives a partition. Phi inverse y gives a partition of this whole of R. Okay, so this will be x1. I mean, whole of Rn. It's the same thing. Okay, I mean what I have written there. Phi of x1 up to xn, then f of x1 up to xn of x1 up to xn. Okay, I think it's clear. The reason is, if you want to do that mod part, I mean, the linearity, it follows immediately when you use this. Now you have the following proposition. I write some of the properties. The first one is E of, I mean, xy. Okay, I should have said that, I mean, you assume the expectation exists and all that, okay? Xy, a random variable, such that Ex, Ey exist. Then Ex plus y also exists. And E of x plus y equal to Ex plus Ey. Similarly, for a scalar, Ex, I mean, we assume that the expectation exists and this is true. And third one is, if you have this condition, this is what is called, I mean, if you say something happens with probability 1, we say it's almost surely happens. So if suppose x is in some interval AB is equal to 1, okay, then Ex is also in this interval AB. I'll just write down some of the properties quickly. Then the fourth one, if probability of x greater than y, I mean, with probability 1, x is greater than y. Yeah, have you done a mistake? Yeah. I'm just going to prove it. Yeah, we are proving it. I'm just writing the proposition. Ex is also greater than Ey. Okay. And fifth one, these are all very easy. If C is a constant random variable, I mean, that is constant random variables, if probability of x equal to C equal to 1. This is what is a constant random variable. It takes the value only C. I mean, okay. Then, of course, it's clear Ex is C, where C is in R. Okay. And sixth one, probability of x equal to y equal to 1, then Ex equal to Ey. Then, if x, y are independent, is equivalent to saying this I have proved, but we will see the proof again. E of f of x, g of y equal to E of f of x times E of g of y. For all x. This is equivalent condition. Okay, let's prove one by one. So, yeah, I proved some of them. This follows. I mean, I did a slightly longer route, but this just. I mean, I stated this because from this it follows immediately. That's why. Okay. Now, if you want to consider E of mod x plus y, which is just x plus y, okay, the summation is in xy in R2. Okay. Then f of xy, xy. Okay. Right. Now, this is just summation x. I mean, we have this xy, summation over xy, x of f xy, xy, plus summation y f xy of xy. Now, if you have the joint density, if you just add it in the one of the coordinate, I mean, summation over x f xy of xy equal to fy of y. Similarly, the summation over y. Okay, we have seen this, no? So because of that, it follows that this is equal to E of x. I mean, I'm sorry. This should be less than or equal to mod x plus. I was using mod x, right? Yeah. I mean, I'm using triangle inequality, and then I mean, this is supposed to be equal to x plus. You understand what I'm saying? You just use that, and immediately you get it. Okay. So this is because of that, it is less than or equal to. This is equal to E of x plus E of mod y. Okay. Similarly, the second one, which is also easy. Okay. Now the third one, x is greater than y. This probability of the third one is what? Third one is in the closed interval, no? Yeah. X is in AB. This is equal to 1. The probability of this is equal to 1. Okay. Then we want to prove the expectation is also in AB. Okay. So let's assume that suppose x is greater than A. Okay, is equal to 1. Okay. Then Ex is equal to summation x fx. Okay. But then when x is not in that interval, this is 0. Fx is 0. Right? When x is in AB complement, then fx x is 0. Because of that. So because of that, this is greater than or equal to summation A fxx, okay, which is a times 1, which is just a. So ex is greater than or equal to a. Similarly, ex is less than or equal to b. You can use the same. Okay, so ex is in b. Still looking at it, is a problem? Okay, it's okay, no? Okay, so third is over. Similarly, if x is greater than or equal to y, I mean, with probability 1, okay? Let's assume that, I mean, usually when something happens with probability 1, we say it's almost surely, okay? So I use this letter, almost surely. Okay, something happens, probability of something, whatever the condition, equal to 1, then we say that something almost surely, okay? We write it like this. Okay, this is my notation. So whatever, something is greater, something is equal to, something is in the set, something is less than infinity, all that. Okay? So x is greater than 1, almost surely. Then x minus y is greater than or equal to 0, almost surely. But by this condition, by 3, ex minus y is also greater than or equal to 0. So this implies ex is greater than or equal to 0. Okay? So fifth one is very clear. If x equal to c almost surely, okay, with probability 1, then it is clear. You just summation, okay, summation x fx. I mean, it's when x is not equal to c, I mean, the function is 0. The density function is 0, so it's clear ex equal to c. So sixth one, if x equal to y, then of course x minus y equal to 0, almost surely. Okay? This implies ex equal to ey. So it's all done. Only the last one I have to prove. Which also I have proved, but some people had, I mean, it was in a hurry. I did in the end of the class. It was in a hurry, so I will do it again. We will do some moment generating function. After that, we'll come to moments. Okay? Generating function. That is it. I think that's the fifth one, sixth one, seventh one. Okay? So x, y are independent. We have two independent random variables. Okay? Then we want to prove that ex, I mean, then this implies f of x and f of g of y are independent. So it's enough to prove that for two independent random variables, it is just the product, just okay. Okay. Now we know that e of xy, it is just a function of two variables, which is equal to summation xy f of xy, right? If you want, you put a mod and other thing. I mean, okay. I mean, you want to do the condition, but let me just write it. Okay, assume that it's positive for the time being, then you do it for the other one. Okay? This is not the right one, but I'm just giving you the idea since we have already done. Now this is equal to, I mean, this is for x. I mean, so enough to prove for x and y this problem. I mean, x and y are independent, then f of x and g of y are independent. Okay, so we enough to prove this. I mean, whatever that condition you want to prove this f of x, g of y equal to e of f of x, e of g of y. Okay, it's enough to prove for x and y. Okay, yeah. The other, so I'm only proving this way. For to prove this way, it's enough to prove this. For the other way, I will prove it there. Okay. So now this is xy into, you know what is that? I mean, this is sum over xy. Okay. This is f of fx of x, fy of y. We know this. Now it follows. Okay. Now this is equal to ex ey. So one way follows. We have to prove the other way. Okay. Now suppose, so the other way is the non-trivial one. Suppose this condition is satisfied, e of f of x, g of y equal to e of f of x, e of g of y for all f and g. Okay. So in particular, we can take what is called an indicator function. Okay. Let x1, x2 is the range of x. Okay, range of x means wherever the points where the density function is strictly positive. The same thing. Okay. Similarly, y1, y2. This is the range of y. Okay. Now you take f is equal to indicator function of the singleton, some xi. Okay. Maybe fi or something if you want. Well, let's take for f. I mean, so a particular fix an I and do this. Okay. And g is equal to indicator function of some yj. Okay. I and j are arbitrary but fixed for the time being. Okay. Okay. Then you notice that f of x equal to, what is f of x? This is just indicator function of xi of x. Okay. And that is just, you are just composing. That is just indicator function. I mean, this is x is a function from omega, which is not here. Okay. F is a function on real line. F of x is a function on omega, the probability space. Okay. Now this is just the indicator function of this set, x equal to xi. You understand the point? I'm saying you are taking f is a function on the real line. Because this point is in the real line, it takes the value 1 here, everywhere else 0. So this is a function on the real line. Okay. X is a random variable means you have some omega. You have some probability space. X is defined on omega. So when you compose f and x, it's a function from omega to real line again. Okay, f of x. Okay. So which is, I'm just rewriting the same statement, indicator xi of x. Okay, that means it is just a composition of that. If you have a omega, then x acts on that. If x is lands here, then it is 1. If it lands somewhere else, it is 0. So which is precisely equal to this. Okay. Similarly, g of y equal to 1 of y equal to yj. Okay. Now you just write the condition. Now if you just write the condition, now if you just write it, e of f of x, e of f of x is equal to probability of that, right? Expectation of an indicator function is probability of that. Huh? G of y equal to 1. This is done. Again, same thing I have written. Instead of x, I have written y. 1 y equal to yj. What is it? If that is clear, this should also be clear. Which is just probability of x equal to xi. Okay, similarly, e of g of y equal to probability of y equal to yj. And e of f of x g of y is just the probability of the intersection. Okay. X equal to xi, intersection y equal to yj. And they are equal. That's what this says. That means that is what the random variables are independent. That's the definition of random variable. So it's clear. Last one. E f of x g of y, indicator function of the product is the indicator function of the intersection. Okay. So that is what I've written. Expectation of an indicator function is just the probability of that set. Okay. Expectation product of the indicator function is just the indicator function of the intersection. So we've done all that. So because of that, it follows. Okay, I think so. These are all very easy. Now we prove something slightly. Okay, from this something follows. Okay, if you have a so we computed the expectation of a binomial distribution, which we can do it very easily here. Let xn, x is binomial. Okay, or you assume x is binomial with n and p. Okay, it has two parameters, right? There is a p and there is a n. Binomial has two parameters, n and p. Okay, now x1, xn are independent Bernoulli. Bernoulli means it's just a one single coin toss. It is just the binomial with n equal to 1 and p, okay, with p, okay, with parameter p, okay, and they are independent. Then x is equal to summation xi, I equal to 1 to n. A binomial is just the sum of n independent Bernoulli random variable. Okay, I mean Bernoulli is given by any indicator function if you want. It need not be coin toss or something. It could be anything. Okay? So now expectation of x equal to summation expectation of xi, right? Because of linearity. And a Bernoulli random variable, it is just the indicator function. So it is indicator function where it takes the value 1. I mean, it takes the value 1 at somewhere and 0 at something else. So it is just equal to, it is just NP. It follows immediately. It need not use any computation. Okay. Let's see another example. We have already computed for geometric distribution and other things, the expectation. So let's do it for hypergeometric. The nice thing is we need not even know what is the density function of hypergeometric to compute the expectation. Okay, it follows more easily. Okay. Hypergeometric is what? You have n something, n items, something. Okay. And here out of this n is of one type. Okay, type 1. And n minus n is type 2. Another type. Or not type 1. Okay? Another type. Then you make a choice. You choose out of this. I will write the formula itself. Okay? You choose k of them. From this n, you choose k of them. Okay? And the hypergeometric is to get type 1 r times, r of them. Okay? So which is just out of n, it should be r. Out of n minus n, it should be k minus r. I think I have written it correctly. This is the hypergeometric, the probability of x equal to r. Okay? This is hypergeometric distribution. We have already seen this. Okay? We need not even know this to compute the expectation. Okay? Okay. So what we are doing hypergeometric is we choose k. So we do it. No, we choose it k times. We draw the. I mean, we take something. A box has some n items. Okay, say some k small n red balls and n minus n some other ball, some blue ball or something. We take something, notice it, and put it back. The other experiment is independent. It need not be. I mean, independence does not matter here. So you with replacement, you just choose another ball. Okay? So you are just doing the so x1 x k is you are drawing k items from there. Okay, there are big n, small n, and you are drawing k items. Out of that, the probability of getting r items, r of type 1. Okay? So you just do the experiment only once. Assume k equal to 1. I mean, xi, x1, x2 up to xn are with k equal to 1. Okay? And they are independent. I mean, it doesn't matter. Independent doesn't matter. Then this x is nothing but summation xi. I equal to 1 to k. Right? You select ball k times. You do it the first time, put it back. The experiment is you do it second time. It has the same probability to get it again. So the probability, so this e of x. So I'm saying that you need not even know that formula. Okay, this is equal to summation exi. Okay, but exi is just getting a type 1 item out of the n item. Okay, which is just I mean, you have no what is it? No, the p is given by that. No, p is given by there are n type 1. No, so n by n, right? N by n. Okay, so you do it k. I mean, so this implies e of x equal to k n by n. So you need not even know that formula. You can directly compute it. The expectation can be computed directly. Okay. Now I want to prove a formula. So from here onwards, we will consider only integer valued random variable. I mean, positive integer, non-negative integer valued random variable. Okay. So this is a proposition. Let x be from, I mean, some omega somewhere, and it takes values in 0, 1, integer value. Okay. Then the following formula may be useful at some point. Ex is equal to summation. If you just know the distribution or something, so n equal to zero will not come. I think. Let's just write it. Let's see what we get it. Yeah, that is anyway one. EXI. EXI is you have n items. Okay, n of type 1. So the probability of getting type 1 in one draw is n by n.
But that's small enough type 1.
Yeah, small enough type 1, n by n. Yeah.
But each side is probability times the.
No, EXI is just one draw. You are doing k draws. So in any draw, the probability of getting type 1 is n by n. Okay. In k draws, it is just the, I mean, it's not the probability, it's the expectation. Probability is different. Yeah. Okay. So the probability is n by n, and that is the expectation. You call it 0 or 1. That's what you want to know. I mean, xi is 0 or 1. Probability of getting 1 is n by n. Okay. Xi is 1 if you get the type 1. Xi is 0. You have to define the random variable. Okay. Xi is 1 if you get type 1. Okay. Equal to 0 if otherwise. Okay. Then it is the summation of that. Now it's clear. Okay. So this is equal to, I think I remember it correctly, but while doing, we will see, which is just probability of x greater than or equal to n. This formula can be generalized to integrals and other things, but let's just write it. Okay. Expectation x is some integer valued random variable. Then expectation of x is this formula. Summation probability of x greater than or equal to n. You sum it from n equal to 1 to infinity. That's all. Okay. Proof. Expectation of x is equal to summation n equal to 0 to infinity. But then x equal to 0 means it will be 0. So n equal to 1 to infinity. Okay. I mean, at 0, when you multiply by 0, it's going to be 0. So n equal to 1 to infinity. Okay. Then n times probability of x equal to n, which is equal to summation n equal to 1 to infinity, summation m equal to 1 to n, probability of x equal to n. I mean, you just sum it n times. Okay. Here, each term is summed over n times. It's the same term. Okay. M equal to 1 to n. There's nothing. Yeah. Now you should tell me whether this is okay. M equal to 1 to infinity, summation n equal to m to infinity, probability of x equal to n. Yeah. Is this okay? It's okay to everyone? So, see, what happens is the following. Oh, I should move to the next. You are summing over two variables, even if it is integral or something. You have n goes like, I mean, you have n going to 1 to infinity, m going to 1 to n. Okay, so for it's like this. it goes up to n like this. Okay. So you, yeah, goes up to n. N. This is n. Okay. N equal to 1, n equal to 2, like this. This is m equal to 1, m equal to 2, up to n. That's what the sum I'm saying. First sum. Okay. So when you sum, what happens? So you first take this and then go like this, go like this. Then you go like this, right? Right? That's what you do. On the other hand, you want to interchange the sum. When you interchange the sum, n will go from here. I mean, when you interchange the sum, you just have to m. I mean, first n. I mean, initially the m is in the first variable. Okay, m equal to 1 to n and n equal to 1 to. That's how it goes. Okay, so it will just first you will sum it over n and then do for each n. Right? This is how you sum. Instead, you want to sum this way and then you go up to infinity and then sum the next one. Each one starts from there. That is precisely the next return. If you write this, it's clear. Okay. I hope it's clear. So what we have is summation m equal to 1 to infinity, summation n equal to m to infinity, m equal to n to infinity. Yeah, probability of x equal to m. Okay. N equal to n equal to m. Sorry, and that's what makes sense. First summation is m, second one is n. That's right. Yeah. Now this is same as summation n equal to 1 to infinity, but then m to infinity means this is just probability of x greater than or equal to n. Okay. M equal to 1 to infinity. It starts with 1. Okay. Now we see whether you have m or n doesn't matter. This is what we want to prove. Now we had n there, doesn't matter. M or n are same. It is just a summation. Huh? M equal to 1 to infinity is probability of x greater than or equal to n. Greater than or equal to m. Yeah. Sorry, this is m. Sorry, sir, not n. You start with m, no? So it is greater than or equal to m. Sorry. Yeah. That's all. Okay. Now we'll define what is called moment generating function. Yeah. You can discuss with me if you have mathematics to discuss. Okay. If it's not mathematics, you can go out and discuss. Okay. So next we want to define what is called generating function. If you have a random variable, x is a random variable, x is a integer valued random variable. Okay. X is a function from probability space to integers, non-negative integers. Sorry. It's for non-negative integers. Okay. Then phi of x, phi x at t, this is what is called generating function. Okay. So which is e of t power x, which makes sense. I mean, it's just an integer, so tx, e of tx, expectation of tx. Huh? Okay, this t power x, t is a number, t is between 1 to minus 1. Let me write what it is. This is equal to summation n equal to 0 to infinity. Okay, because it's integer value, n equal to 0 to infinity, probability of x equal to n, or this is just fxn if you want. Fx at n times t power n. And this series exists. I mean, txt, if you just, I mean, e t power x, e mod t power x, okay, that is less than or equal to summation. This is just less than or equal to 1, right? So which is just summation n equal to 0 to infinity fxn. This is equal to 1. Okay. So etx exists. Okay. So that's why this definition. I mean, this is the definition. And the definition is justified because of this. Etx mod tx is equal to summation is less than or equal to. I am just taking the forgetting the t power x, which is less than or equal to 1. Okay. This is just a power series between -1 to 1. So the immediate remark is, if you have two random variables, then of course random variable can be different, but it can have same density function. So this depends on density functions only. So it says only about the density function. Then fx of n, fx equal to gx as functions. As functions, they are same. Sorry, fx nonsense. fx equal to fy. Sorry, fx equal to fy. Okay. If two random variables have the same generating function, then they have the same distribution or same density function. Okay, that is just by equating the coefficients, which you can do in a power series. If you have two polynomials are equal at all points, they are same. But two infinite series, power series like this, they are same for all t between, I mean all t between -1 to 1, then they are same. Just by differentiating, you will find it, right? This is because phi xt equal to phi yt. Okay, that means the power series for all t less than or equal to 1, greater than or equal to -1. Okay, now you just differentiate it and evaluate at 0. Okay, d by dt nth. You take the nth derivative, n equal to 0 means it's just the function, okay, of phi x at 0. Okay, same thing. Py again at 0. This implies that fn fx n equal to fy or n or n-1, I'm not sure. Yeah, I think n. Yeah. You take the nth derivative and evaluate at 0, okay, then you get this. All these things are n times differentiable because it's a power series. They are differentiable. You can see when you have this kind of power series, you can take the derivative. We already discussed this once. I'm not sure when was that. When we were, I don't know. We were talking about something. Huh? At t equal to 0. Yeah. What is that? D to the power n. Yeah. Yeah. Otherwise, it doesn't make sense. Yeah. Yeah. I want to put the operator times n. That's what I want to mean. You apply it n times. You differentiate it n times. So this is clear. Huh? N is? Okay. So, and let's do this proposition. X, Y are independent. Because when we talk about independent, they are defined on the same probability space and satisfies the condition of independence. Otherwise, it doesn't make sense. Okay. Then phi of x plus y is equal to phi x times phi y. Pointwise. This means when we write multiplication of functions, means pointwise multiplication. X plus y. I said plus y, but I don't know. I mean, it's almost same as the density function, which multiplies. Why is it? Y evaluated at 0. Other terms will become 0. No, only one term will survive. You don't differentiate up some substitute 0, you'll get the constant term, which is the density function at 0. You differentiate it once, constant term will go. The t power, yeah, that's all. Yeah, that is precisely probability of x equal to n, and that is the density function. So if x, y are independent, then phi x plus y equal to phi x times phi y. You want to prove this, okay? Which is just multiplication. See, even though it's written as a power series, it will become a function. Okay, we will know the function e power t using Taylor series. We will know that it's some. I mean, it's always a function. What I mean is, it will become a familiar function. Okay, I mean, it's anyway functions. Function is just abstract thing. Okay, what I mean is, it will become some familiar function. Okay, then we can multiply them and compute it. That's why I mean, you want to apply it somewhere, right? See, that is a problem when you come, I mean, when you study mathematics later, you know what is a function is. But in general, people will think sin x, cos x, these are the functions. They will have a abstract function means they will not have any intuition for that. So I am saying in that sense, it will become a function means it will be some familiar function. That's what I mean. I didn't hear. Okay. Okay. So you want to compute phi x plus y. Okay. At t. Okay. T is between -1 to 1, which is equal to summation n equal to 0 to infinity f x plus y at n t power n, right? So I'm just writing the definition, which is equal to n equal to 0 to infinity. We know what is f x plus y when x and y are independent. We know that, which is just the convolution product. Okay, so which is just f x, which is again summation m equal to 1 to, I mean, it is a summation. That summation is over real line, but it will make sense only for these things only because it's non-negative integer value m equal to 1 to n, okay, which is just fx at m into fy at n minus m. Okay, then the whole thing t power n. Okay, that t power n, I split it like this: t power m, okay, and fy at n minus m, t power n minus m. Okay, I can write it like this. Okay. This is okay, no? So now we take the summation, again the same thing, m equal to 1 to infinity, summation n equal to m to infinity. Okay. Now fx m t power m, okay, into fy n minus m t power n minus m. There is no n here. Okay, so you can take it out of the summation. Okay, so this is just equal to summation m equal to 1 to infinity fx m t power m. Okay, let's not do that. Then you have the summation. This is n equal to m to infinity. Okay, fy n minus m t power n minus m. If you look at this sum, it actually starts from 0 to infinity. It goes from 0 to infinity. Starts at n minus m, but it starts at n equal to m. Okay, so when equal to m, this is 0. M really doesn't matter here, right? N has no role here. It is just change of variable. It's like when you integrate, Riemann integrate, you translate it. If you integrate it, okay, change of variable kind of thing. Okay. So this is just m equal summation m equal to 1 to infinity. So this is just, I mean, I just write it phi xt times phi yt if you want. This is equal to summation n equal to 0 to infinity fx n t power n. Okay. Okay. This is same as that. So this is equal to phi xt phi yt. Right? This is same as this. You want me to write another step? this particular term is equal to summation n equal to 0 to infinity fx n, or you write it as k, okay? Substitute k equal to n minus m, okay? K equal to 1 to 0 to infinity fx k t power. That will be easier. Okay? To change the variable, substitute k equal to n minus m, you get this, okay? Pxy. That's done. Now let's do some example. Maybe we'll stop. Fast.